Can everyone see my screen? Yeah, I hope. Hello, everyone. This is the another session of book club, and this is the second part of consistency and consensus. So before we begin, let's do a quick recap of what we discussed last week. So last week we discussed about linearizability, right? So basically, linearizability is the strong consistency, which is the C in the gap theorem, right? And we discussed what makes a system linearizable. so, uh, so a system is linearizable if we have multiple nodes in a let's say if we have a distributed system which has multiple nodes, and then if we write something to that system, when we read, if one of the nodes has seen the latest value, then any subsequent nodes should also see the latest value, right? So once someone has seen the most latest value, then everyone following it should also see the latest value, right? So in this way, the entire set of distributed nodes, those replicas, will behave like a one system. It will behave like if we have only one node in the system, right? Because we get that consistent, strongly consistent view of our system, right? So so like I just want to give two examples. So here, like, let's say if this was the database, and if someone has written x equals to 1 to the database, right, then and then this operation was performed, and finally the client got okay response, right? And this is the point where the data was actually returned to the database. Now there are two situations. One is after this client got okay response, right? At this point, this client knows that its value has been written, x equals to 1 has been written, right? So now after this point, everyone should, if anyone is reading, it should read the latest value, right? Because this client has in a way read the latest value at this point. It knows that this is the latest value. Another example could be, let's say I was writing x equals to 1, right? And at this point, the value was written. I have still not got the okay response, but someone else has read the value and his request hit at this point, right? So now he will see the latest value. So now, even though I have still not got okay response, but even before this point, after this point, everyone should see the latest value, right? So basically, when anyone knows about this latest value, following it, everyone should know the latest value, right? So this is what we discussed last week, that how would we know that a system is linearizable, right? And then we discussed what kind of systems need linearizable storage, right? So basically, if we don't have linearizable storage, what we're saying is that if we read a value, right, you are not ensured that you will get the latest value. You might see latest value for some time, and your system might become eventually consistent, right? But like, if you want to, if you if we, what kind of systems would need this linearizable storage? So any kind of system where we need this uniqueness, right? When we need one of something, right? So in these one of something scenarios, uh, basically, if we are seeing the stale values, right, we can make wrong assumptions. We can, based on the stale values, we might make some wrong assumptions, and we might not actually get that unique value. We might do something which generates two values or something, right? Like the scenarios of unique username, or like a scenario of obtaining a distributed lock where only one of the one of the system should get the distributed log. In these kind of scenarios, it's very important that the system should be linearizable so that we don't see a stale value and we don't make a wrong assumption based on that stale value, right? Uh, then and then like the last thing is, what is the cost of linearizability? So basically, uh, so we know this cap theorem, right? So C is the consistency, which is this linearizability, right? That then A is the availability and P is the network partition tolerance. So basically, if we want, so all our distributed systems, they need network partition tolerance, right? Because these distributed nodes are connected through network. And we have discussed in the last chapter that these networks are not reliable, right? They may have unbounded delays, there might be network failures. So any distributed system, it needs P, right? So now we have the option to choose between C and A, either strong consistency or availability. So if we are using strong consistency, if we are using linearizability, then our availability will take a hit, right? So this is the cost of linearizability, that if you want to make a system linearizable, you have to pay for the availability, right? Okay, so moving on. So now in the last chapter, we have discussed serializability, right? Not last chapter, last to last chapter, the transactions chapter, we have discussed this concept of serializability. And then in this chapter, we are using this term linearizability. Uh, do you guys also find yourself confusing between these two terms, serializable, linearizable? And does anyone wants to tell the difference between these two so that we get a hang of this transaction chapters as well? So this is how like I think about it, and this is how I try to remember it. So basically, serializable, right? What is the meaning of serial? Like if you look the dictionary meaning of serial, serial means something that happens one after another, right? Something which is happening in sequence one after another. uh, and serial is opposite to concurrent, right? Basically, concurrent means things are happening together, and serially means they're serially one after one happening in order. So this serializability is required when concurrent transactions are happening, right? And you want to ensure that those concurrent transactions behave like they are happening serially, right? That one transaction should not step into the foot of other transaction. So those scenarios. So that's why in the transaction chapter we discussed the serializability, that if concurrent transactions are happening, we need to ensure serializability, right? Linearizability, right? So what is the meaning of linear? So linear means involving one dimension only, like we have used this linear, right? Linear means in one dimension there is line, or like we use this linear algebra, right? So linear algebra is where there is only one variable involved. So it means that only one dimension is involved. So if you think of a replicated system which has replicated nodes, right? So basically, each node of that replicated system might represent a timeline of your data, right? Because if those replicas are not in sync, one node might represent that at some point the value was this, now the value is this, now the value is this. Some other replica, if it's not in sync, it might have values up till some point, right? So if you look at the timeline, all of these replicas are might represent different timelines. So a linearizable system means that the entire system is behaving as one timeline. There is only one timeline. And um, basically, uh, so so like there is nothing like concurrent happening in the system. Everything is mapped on that single timeline. Everything is happening one after the another, right? So that is the concept of linearizable. So that's why this linearizability is used in the system where we have replicas to give us these guarantees that these replicas are not behaving differently. They are not behaving as different timelines. They are behaving as one unique view of that entire system. Right? Okay. So yeah. So let's move on to the next section of this chapter, which is ordering guarantees. Okay. So why do we need ordering of the events, right? Why do we need ordering guarantees? So, so one very common scenario is causal ordering, right? Causal ordering of the events preserve the causality. So that means that we we would want to order our system in such a way that the cause always comes before effect, right? If someone asks the question, and so if we have two events in the system, one was the question and another was the answer to that question. So the events should be ordered in such a way that question always comes before the answer, right? So this is the scenario that there should not be any problem in the distributed system, that we have somehow stored the events in the wrong order, that the effect is coming before the cause, right? So that is one scenario, that for causality we need this causal ordering scenario. Uh, Another scenario is total ordering, where every event is ordered. So like basically every event has some order, and there is nothing like concurrent events, right? No two events are concurrent. Everything is ordered, uh, and that is called total order, and this is used to implement total order broadcast. So like to take an example, so let's say we have these four events A, B, C, D, right? So if we are saying that these events are causally ordered, we might say that B happened after A and D happened after C, right? But we don't know about the sequencing of like A, B, and this C, D, right? They could happen concurrently, or they, like, we don't know. So this is like causal ordering, that we at least definitely know that what thing happened after and what thing happened before, but we are not guaranteeing that we will order all the events of your system, right? But if we want a total order, so a total order would mean that the events are ordered like this, right? That everything, we are saying that D is the most latest, then B, then C, then A, right? And so this is the total order of the events, right? So and this kind of ordering, total ordering, is needed in total order broadcast. When we move to total order broadcast, we will see that why we actually need total order broadcast. So yeah, so these are the scenarios where we need ordering of events. So now moving on. So how do we implement this causal ordering, right? So we discussed two types of ordering: causal ordering and total ordering. So basically, if we want to order the events, it is very simple to order the events in this single leader replication model, right? Because in single leader replication, basically the leader decides what is the order of the events, right? And then the leader just passes on the replication log to other nodes, right? So so basically leader will queue the events, that leader node will queue the event, write events, and it can order those events in the sequence in which it saw those events, right? So, so that's why in single leaders systems, it's easier, right? But the problem is when we have these multi-leader and leaderless systems. So in these systems, because multiple nodes are concurrently accepting writes, so we don't know like between two writes how to order them, right? And in the last chapter we have discussed we cannot purely rely on timestamps because timestamps are not synchronized between various machines, right? So even though if you compare the events between two nodes using the timestamp, and you might see that the timestamp on one of the node is more, but still the event could actually have come before because of the problems in the clock synchronization between those two nodes, right? So, so, uh, so basically, to implement this causal ordering, we need some generalization of version vectors. So if you all remember, uh, I think few session backs, we discussed this version vectors. So basically version vectors are used to track the causal ordering for a particular key, right? So for a particular key, basically we maintain a version, and the vector means that each each of the replica for each of the replica we maintain a version. So that's why in each of the nodes we keep a version vector, which is the version of that key in that node and version of the key that has seen by that this node in another node in all other nodes, right? So that was the version vector. So now here version vector was used to track the causal ordering of events for just particular key. But if we want to implement this causally ordered database, then we need to track this causal dependencies for entire DB, right? We want to track the causal ordering between different keys as well. So and now if we want to track these causal dependencies for entire database, it could be expensive, right? Because if you have to track that what is the causal ordering between all the events in the database, it will be expensive, right? So like some simple things we can do is we can use these sequence numbers, right? So sequence numbers would be used in such a way that the sequence number which is lesser on one node will tell that this event happened before, and the sequence number if it's more, we know it's uh, we know that this event happened later, right? But sequence number, so later we will discuss that how we will use this sequencing number between various nodes. But if we use something like sequence number or some kind of these vectors, they will not only provide us causal ordering, they will provide us we can use sequence number, and they provide the total order, right? So these sequence number will provide the total order, because sequence number, if we have a sequence number 1 2 3 4, we can order this, and it is not just providing the causal ordering, it is providing us total ordering of the events, right? So uh, so 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 basically let's discuss how we can actually implement total ordering, because if we can implement total ordering, then causal ordering will be a subset of it, and we can get the causal ordering in some scenarios from the total ordering, right? So one of the ways to get the total ordering of events is Lamport timestamps. Uh, so this is what Lamport timestamps are. That so let's say you have two nodes. This is node one. This is node two, and there are two. We have two clients which are writing to these nodes, right? So basically, in Lamport timestamp, we will store two values. One is the counter, and another is the node ID. Uh, counter is storing that number of operations a node has seen so far. And node ID is node ID of that node, right? So initially both the nodes have seen 0 operations, right? These nodes have not seen any operation. Now, if a client and also like the nodes will also maintain how many operations they have seen, and the client also needs to know that how many operations that node has seen. So initially, like when we start, both of them have 0. So it will make some write to the database. So now this node will increment because before it has 0, now it has seen 1 write, right? So that's why it will return this important timestamp, which is it has seen 1 as the counter and node ID is 1, right? Similarly, this node has also not seen any operation before, so it will return 1, and the node ID is 2, so it will return 2. And now it will return this. So now this client knows that this node has seen 1 operation. So it will make a write request saying that, like, I know that you have seen up till now 1 operation. So, uh, so, so then this will also see that before this it has seen 1 operation. So it will increment to 2, similarly to 3, similarly to 4, right? The scenario here where this client will say that, so after this request, it will say that I have seen up till now 1 operation, like I have seen 1 operation. So it will send the request with 1 operation. So the node will take the maximum of what the client has sent and what it knows up till now. So the client has seen 1 operation, but this node has seen 4 operations so far, right? So it knows that its value is more latest. So it will make this as 5, right? Because 4 plus 1 is 5. So it will return that I have seen 5 operations. Then now this node knows that it has seen 5 operations. So then when this will make a request to this node, it will take the maximum of what it has seen so far. It has seen 1 operation, but the client has seen 5 operations, right? So it will store now 6, right? And it will return 6, 1, right? And similarly, at this point, it will write, it has seen 4, so it will write 4, but the node itself has seen 5 operations, so it will return 6, right? So now, basically now we have these various timestamps 1, 1, 6, 1, 5, 2, 1, 2. So how do we order these in timestamps? So basically the logic is that you compare the counter, right? The value which has more counter, which is greater counter, is the more latest value, right? So basically this 6, 2 is greater than 4, 2, right? But what happens if the counter value is same? Then how do you compare two timestamps? So basically the meaning is that if the counter value is same, then 2 of those timestamps happen concurrently, right? And so then, like, what Lamport timestamp is doing, that it is giving ordering that the node which has the node ID which is greater, its timestamp is higher. So like basically if you compare 1, 2 and 1, 1, so this timestamp is higher. So although basically they could have happened concurrently, like because these two nodes have not talked to each other up till this point. So maybe these two events have happened concurrently, or they happened at this different time, but these two nodes have not talked to each other. So now if they want to order, because they don't know about these events, so basically they will order them on the basis of node ID, that the one which has node ID higher, that will be taken as a higher timestamp. So in this way, we have created a total order of the events, right? We know the entire order of these timestamps. We can put them in like we can put them in a total order. Uh, but the uh, but the problem is, so with the Lamport timestamp, the problem is that uh, basically you can compare the order of the events once you have got these timestamps, right? When you were making a write request, these nodes were not talking to each other. They were just making a write. They were not talking to each other and comparing whether there are two concurrent requests or not. So this is something which we will see in the next section, that can we use this total ordering of events to provide the uniqueness guarantee. So we discussed that in linearizable systems, one of the good use case of linearizable systems is to provide uniqueness guarantee. So now we so now we have this total ordering of events. Can we use this to provide the uniqueness guarantee? So so can I use just this total ordering of events to provide uniqueness guarantee? uh, So no, we cannot, right? Because the point is that uh, like for uniqueness guarantees, like these nodes should talk to each other, right? These database nodes should talk to each other, and they should decide that which write request to fulfill, which write request not to fulfill. Here, although we have created a total order of events, but this total order was created once we got the response back, right? When we were making the writes, these nodes were not talking to each other and not ordering themselves. So that's why when we send a request to node, we don't talk to other nodes and compare the value with other nodes to check if there is any concurrent request. So this just gives the ability to order the events after they have happened. So then now how can we use total ordering to provide uniqueness? Uh, so there is this algorithm, total order broadcast. So is anyone saying something? Okay. So we can use total order broadcast to to help us provide these uniqueness guarantees, right? Because up till now we discussed just this total ordering of events. These nodes don't talk to each other. So what is exactly total order broadcast? So in total order broadcast, we are not just like having the order of the events, but we are also broadcasting that order of the events to all these nodes, right? So basically, total order broadcast is exchanging messages between nodes, and the algorithm should satisfy two safety properties. One is reliable delivery. That means that no messages are lost. So every node, it should get the ordering of events. And even if that node is down for some time, total order broadcast protocol should keep on retrying, and it should reliably deliver the message to all the nodes in the system, right? That is the one safety property expected from this total order broadcast. The other is uh, totally ordered delivery. So that means that uh, the events should be totally ordered, and that order should be fixed, right? Every node should agree on that order, and there should be that one order between all the nodes, right? So this order of messages should be fixed at the time of delivery, right? And if a protocol can satisfy these things, then it is a total order broadcast, right? So now what we're saying is, not only we are like ordering these events, we are also broadcasting the order to all the nodes, and that is total order broadcast, right? So now our events are ordered, and now we are broadcasting the events to all the nodes. Now can we provide the uniqueness guarantees? Now can we build a system that provides uniqueness guarantees from total order broadcast? So can we use just this total order broadcast to implement uniqueness guarantees? Uh, Again, the answer is no. Uh, because uniqueness guarantees need linearizability, right? That means all node should have that consistent, strongly consistent view of the system, right? So total order broadcast only tells that these async messages are guaranteed to be delivered reliably and that order will be fixed. But we are not, there is no guarantee that when these messages will be actually delivered, right? Uh, so just using total order broadcast will not, we will not be able to implement uniqueness guarantee because we don't know that whatever is the ordering of the messages when it is delivered to all the nodes, right? So but we can use total order broadcast and we can build something on top of it to provide uniqueness guarantees. So what is that? So so basically uh, so basically a way to do that is so like all the messages when someone want to uh, provide this uniqueness guarantee, and let's take the example of unique username, right? So if someone wants to write a unique username, so it will send the request for that unique username to the node, right? So that node, it will write that log, it will append a message to the log that this username that we want to basically we want to reserve this username, so it will append this log and then it will make the total order broadcast of that log that this username is needed, right? And now basically with total order broadcast, this log will be delivered to all the nodes, right? And in the meanwhile, it could have happened like some other nodes could have concurrently got the request that we also want to reserve this username. But what we are saying with total order broadcast is that like there will be just one order of the events, right? So all the nodes will agree on that one order, right? So before successfully accepting the right of that user, if you wait for the uh, total order broadcast log to come back to you and you see that your log was the first log in this system which was asking for that username, and then you implement this algorithm in such a way that the node whose log is the first log asking for that username, that request will be successful and other request will be aborted. Then you can ensure that basically a unique username is given to only one request, right? Because this order will be maintained between all the nodes. And the problem where we said the total order broadcast, we don't know that when these messages are delivered. So that's why to avoid the problem, we are waiting the message to be delivered back to us after talking to all the nodes. So we have waited. Uh, for all the nodes to agree on that ordering, and when everyone has agreed on that order, now I'm making a decision that if my request for that username was the first one in the log, then only I will say yes, and then only I will respond success to the client, right? So basically, like if you think about it, the way we are approaching this problem is like we are kind of implementing a consensus kind of thing, right? That uh, this node, it is proposing a kind of ordering, right? And then we are waiting for a response back, like we are broadcasting this order and we are waiting the response back, and if everyone kind of agrees that this is the order, and I can see that I am the first one in that order after the consensus from everyone, then I am only making a decision, right? After that broadcast from all the messages. So
One question. Before actually writing to, it's broadcasting to all the other nodes, and it is only actually going to commit once it receives all the acknowledgement from all the nodes.
once it yeah once it receives back the order of the log, what is the log, so basically read through log by appending message, reading the log and performing act, oh sorry, not this. So append a message to the log, uh, indicating the username you want to claim, and then read the log and wait for the message you delivered to be delivered back to you. Check for any messages claiming username you want. If your message is first in the log, then append is successful. Uh, so,
So my doubt is like, is it like for that response to come back, it should be like it should have a response from all the other nodes. So like node one, there was a 5 nodes, it broadcasts to all the other 4 nodes. So all the other 4 nodes, when response back, only then it will be able to write, or if it gets from a particular number of nodes, and then it can actually write and like commit for that particular unique username.
mhm. Yeah, I exactly don't know how this total order broadcast is implemented. I don't know if if it will just get back one response or every node will be respond. I think like uh, does anyone else knows that will it be?
Like what I was thinking, like even I don't know how it is implemented, but based on this understanding, uh, because the definition says that each message will be delivered to all the nodes in the system. So when this log is appended, so I want this particular username, that message will be sent to all the nodes in the system. So that means that all other nodes got that message, and if even if myself get the same message first, then I can claim that username. But
Mhm.
let's say there is another node in the system which is concurrently uh, want to claim the same username,
Mhm.
then there is a probability that the both the nodes, either of them will get like since the total order broadcast says that all the messages will be delivered in the same order, so all the nodes will either get A or B. So in that way it is uh, like the claim the concurrent requests are handled.
Mhm. Mhm. Yeah, yeah, yeah.
But all the nodes will get only one message for one from one node.
Mhm. Okay, yeah, okay. Yeah, even I also think the same. So yeah, every node will get back one message, not I think not uh, like response back from all the nodes, right? They will get one message, and that is what uh, and it will like basic. So if I am if I am the sender of the message, so if I am the sender of the message, right, then the other nodes will be receiving that one message from me, right? But here we are saying that the sender has to wait for the response back uh, to receive that log back. So in this case, who will it be receiving the message from? Will it be receiving them? So we are saying, right, and wait for the message you delivered to be delivered back to you. So who will be delivering back to me? Is it like one particular node or is it all the nodes? Right? This is the question, right?
Yeah, yeah, yeah.
For the
Because
total
every node, yeah, go ahead.
broadcasting, I think it have to wait for all node, right? Because
every node have to agree. If one node or a few node not agree, then it's not total order.
Okay. Uh, so, okay. So I think what's happening is like we are appending the message and then we are reading the log. And yeah, so that read operation is also a total order broadcast, right? So in read also, like, yeah, so like that we will be asking every node and then, yeah, so the if nodes have different log, yeah, so read the log, and whose log are we reading? Are we uh, so if different nodes have different logs, then who? So if we are saying that we are waiting for the value from all the nodes, then if different nodes have different logs, then whose value will we take? Right, that is another question.
Like we look at the Lamport timestamp, right? I think was it like the one if the timestamp are equal, then we pick the one with
With the
highest ID.
higher node value, yeah,
Yeah.
higher,
No,
no,
not highest. No, yeah, high ID, node ID.
node ID, yeah, higher
Yeah.
node, yeah.
Yeah, I think all of them have to agree, because if you think about you want user one want to claim A, and user B want to claim B, username B, and happen that half of the node agree with user A, and the other half of the node agree with user B, and that would be not total, right? Everyone have to agree.
Yeah, I think to understand this better, we would need to understand what these protocols are, what the total order broadcast protocols are. And yeah, and actually, and like I was briefly reading about it, like there are many total order broadcast protocol, like there are like at least more than 15 total order broadcast protocols. And I think that's why in this book they have not specifically mentioned about any one of the protocols, but I see that it's very important to understand one of those protocols. Exactly understand.
So one way what we do is in terms of ordering, right? If two are requesting the same username, right? So before we respond, we always have a sequence number in which the order of events come in, right? At any point, even though both are requesting for sequence number AB or username ABC, right? And even though two different events came at the same time, we'll take the order of events, and if both pick ABC, and then after we write first one, we create a log of it, or at a central place, and before we do the response, we'll check that, and to make sure that so first one came and took ABC and responded, right? And then second one, when before it says the response is okay, it checks the central place. If the ABC is already taken, even though it says that okay, then it will do a retry and say either it will suggest with ABC is over, try something else, or it will say that ABC is not available. So that is one way where even you use serialization of counters to validate, like how lamppost, right? You take that counter and you maintain the counter and ordering in a, after it's successful in one place, and use that to validate the second response.
Okay, yeah. So are you suggesting like some kind of a single leader kind of systems where that one single leader is a central piece of truth? So every time you want to order something, you're first going to that single leader.
Yeah, after final commitment, after final write access, whoever gets to write in that final one gets to keep the username. That's one point. You may have multiple nodes, right, of different areas, but when it happens in the domain names, like someone says this, I need to get www.cnn.com, right? Multiple people are trying to pick the same domain names. So at that point, whoever picks the DNS and then registers it, right? Once you register the domain name, you may be at the payment stage or credit card stage and everything. 2-3 people are doing, but one who registers first and the payment is approved, that will get registered to the DNS.
Yeah.
And once the DNS is registered, second person may almost be done, but he'll check with the DNS before he gives the final okay. And then he says, okay, sorry, even though you were the first, but your payment didn't go through, so someone else took it.
Yeah.
Even for hotel reservations and everything, the same logic. Even the one room is there, you may pick it, but someone else took it. His payment went through, and so he'll check. Even at the end, you will again check that and respond.
Yeah. Okay. Uh, uh, so yeah, basically this implementation which they have talked about, like waiting for the messages to be delivered. Yeah, we need some consensus from all the nodes, and yeah, and we have to exactly see how that is done, and probably it might be discussed later in this book. I have not gone through the entire chapter, but yeah, let's revisit this. That how is it waiting for the message to be delivered back to you? So, but basically, like once you have appended the log, and then you are waiting for that message to be delivered back to you after the consensus from all the nodes, then you know what is the final agreed upon order from all the nodes, and then based on that you are taking the decision, right? So this is how we use total order broadcast to implement these uniqueness guarantee, right? uh, so so now like there was one brief explanation of how we can implement this total order broadcast, but the assumption is that we have a linearizable system. So if we already have a linearizable system, how can we implement total order broadcast? So if we have a linearizable system, then it's easier, right? Then what we can do is, for every operation, for every compare and set operation, we give it a increasing ID, right? And basically, like because we know the ID of the operation like before, and then when the next operation comes, we like we can increment that message ID, and so basically, and now we will be always sending the messages with that increasing message ID. So now, if we want to implement total order broadcast to every node, we are saying that you should be uh, getting the messages in that same sequence ID. And if any sequence ID is missing, then you have to wait because some message is missing. And so basically, then every node will wait for the messages to be delivered in that same sequence ID, right? So, and like how linearizable it is making it easy, because like we have we have a consistent view of the system. So whatever is that sequence ID, right? Whatever the sequence ID we have, that is a consistent view from all the nodes. So we just keep on increasing that sequence ID, and then sending the messages, total order broadcasting those messages with that sequence ID, in the order of the sequence ID. So, so yeah, so basically let's read it through. So assume you have a linearizable register that stores an integer and had an atomic increment and get operation. So for every message you want to send via total order broadcast, uh, you increment and get the linearizable integer, and then attach the value as sequence number of message, sending it to all the nodes. So for every operation, you are also attaching this sequence number and this and this. So every message has that increasing sequence number, and now you are sending the messages with the sequence number attached, right? So uh, so unlike Lamport timestamp, numbers we get from incrementing linearizable register uh, for a sequence, so there are no gaps, right? So every basically every message, it will have that increasing sequence of numbers, right? uh, so now like so, so yeah, so as we discussed, so now then every node has to wait that if there is some message missing with the sequence number. So let's say if a node has got a message with sequence number 5, and if now a node gets a message with sequence number 7, then it knows that there was some message with sequence number 6 which is missing, so it has to wait for that. And so basically in this way we will keep all the messages ordered, that 5, 6, 7, right? That order will be maintained. And uh, and so the requirement of total order broadcast is, right, that the order should be same between all the nodes. And we have to keep on retrying. So if a node has not received that message, it will keep on retrying to get the message until it finally receives that message, right? Again, this was also very briefly explained, like, and yeah, and I don't know if there is any like if we actually have a linearizable system already, how, like, what are the scenarios in which total order broadcast is used. But yeah, okay. So now, like, this is the brief tease out of what are the things required to build a distributed transaction, and how we can build consensus from this total order broadcast and linearizability. So now let's move on to this topic of distributed transaction and consensus. So in today's session, let's discuss about distributed transaction, and probably we can discuss about consensus in the next class. So
Abhishek, one question before we move further.
mhm,
Um, uh, the question is related to Lamport timestamp.
mhm.
So in that picture, the it says the client, right? Can you move? Can you show that picture one time? Yeah. So here, this client will be web server, right?
This client is is it could be like anyone. I think it could be a oh yeah, no, it will be our applications server, because it has to handle all that logic of what is the maximum it has seen so far. Yeah, like
Yeah, yeah. So I was just thinking, like, then because here they says that there are issues with the Lamport timestamp as well. So what are the use cases in which we, if we ever use, in which use cases we can use this Lamport timestamp?
Okay, so Lamport timestamp is giving the total ordering. How? Yeah, what are the scenarios? Yeah, I don't know what. Like, when do we actually use Lamport timestamp? I don't know if like this was mentioned to build some another, like, my understanding is like the concept of this Lamport timestamp is used to build a system on top of it, but I don't know if this Lamport timestamp by itself could be used in some scenario.
Okay, because here they mention like after the concurrent transaction has happened, then we can like define the order.
Yeah.
I was just thinking like where we can use this. Okay. And second question, which I feel confusing here, because earlier we were saying in linearizability, like how we can make a system linearizable by like in the last we were thinking like we will use total order broadcast, but now we are saying like for total order broadcast we need a linearizable system. So both looks like one both needs one another, so I feel it like little confusing.
Uh-huh. So yeah, I think uh, so what he mentioned was that how like there are various ways to implement total order broadcast, and like but like one of the easier way he was explaining was that assume you have already a linearizable system, then how you can easily build total order broadcast. But yeah, but like that's not the only way. Like without, like if you have not a linearizable system, I think a lot of broadcast for that also. And yeah, so I mean, I had the same question what you're asking, that if you already have a linearizable system, then things become pretty easy. The difficult part is like making the system linearizable, uh, right? So I think maybe just like to explain the concepts that he has mentioned, that assume that you have a linearizable system, how then you will just do the part of total order broadcast.
Right, because throughout this chapter I feel like linearizable system it's like difficult to implement until unless we have a synchronization replication.
Mhm.
um, but I am still like thinking like how in real like life scenario how the linearizable systems are implemented. But yeah, maybe there is something later in the chapter.
So one thing, so sorry, jumping back. So your question, right? Why will we use Lamport and timestamp? So one thing which came to my mind is like some ordering of logs, right? So one way you can use Lamport and timestamp is to order your logs. So basically, and uh, like I don't know if you guys have used this scenario where like basically your request goes to one node, right? And then from one node it will go to other nodes, and it will like basically that those requests, multiple requests are reaches different nodes, and then from those nodes they go to those other nodes, right? Now if you want to, if you are debugging an issue and if you want to see like what is the order of events, like how did the events happen in this system, right? So you would want to order your logs, right? And then in that scenario, when you get this Lamport timestamp back, if you use that logic to order your logs, you can actually see how the events happened in your system, right?
Another thing is, let's see, look at node 1 and node 2 in this diagram, right? And we don't know the total order, but you know the total order of will be guaranteed when all node communicate and talk. And if we look at on client A, after the write max equal 1, right? After that, then that's going to be the total order, right? Because after that, let's say what is the max, so far in the system. So at that point, right after max, that we get the total order of the whole system. But then, after we writing concurrent, you say C equals 6, then, that's not guaranteed. So at any point when the whole, everyone communicate and talk, to the single point, and that will give us the total order. And I think that's why we need to have the broadcast, so that everyone agree on it.
Yeah, if we want to agree on something, we need broadcast. Yeah, I agree. But yeah, like I was saying this, that like if we want to just, so basically in this scenario what will happen is we will get this 1 1 back, we will get this 1 2 2 2 3 2 and all these things back. So one advantage of like now sorting them based on this is like kind of ordering them to see like to like a scenario of logs and all, where you want to order the logs just to get a feel of like how, what was the sequence in which the operations happened. And so in here, like they have also mentioned that Lamport timestamps cannot identify if two operations happen concurrently or they happened one after another, right? Because it will order them, it will provide a total order. So it will say that this event happened after this event because the node ID is greater. But like I was thinking, still we can say two, okay, no, we cannot say two events are concurrent. Yeah.
What happens to collisions of broadcast, right? If two clients write at the same time and they broadcast at the same time, which is the first scenario.
Two clients write at the same time and they broadcast this message
At the same time, yeah. So
Mhm.
which one, in this scenario, which one should it take?
So so if we are using any total order broadcast, it will ensure some fixed ordering. So, and that logic or algorithm could be anything. So that logic could be that if something like this happens at the same time, the node ID which has a greater value, that timestamp is higher. So then it could order in such a way that this 1 2 is higher than 1 1.
Yeah, so the client B will get it. So
Yeah,
let's say suppose client, yeah, right? Client B is have a contact the node ID 2, which higher than node 1.
yeah, I mean, if two things are happening concurrently, then you can take anyone first and anyone second. It's just that whatever logic you are choosing, that logic should be agreed upon between your entire system, right? So that's what they're doing with Lamport timestamp. That if they don't know about the things, then they have this logic that it is agreed upon by the system that the timestamp which has a higher node ID, that timestamp will be treated as a higher timestamp. But another thing is like this will not tell if two operations are concurrent, because I see the problem is, so let's say this, so basically the, yeah, I'm little confused here, because we can tell if two operations are concurrent by looking at this first value, right? If the first value is same, then that means two operations are concurrent, right? And but in the, yeah, I mean, but in the book it has mentioned that Lamport timestamps cannot be used to tell if two operations are concurrent.
Is it like it mean the real concurrent? Because I could have think like if we think the node 2 is a winner because it have a higher ID, but it could happen that client A write C equal 1, and much later client B write C equal 1. The client B is still winning because in that case, client B still contact to node 2 which have a higher ID, right?
Yeah, yeah. So yeah, probably something like this, that even if this operation happened much later and they are not concurrent, but like we cannot definitely say these two operations were concurrent, right? Because this could have happened much later and it could have been the first operation on this node. Still, it would have got the ID 1, 2, right? And so then if we compare 1, 2 and 1, 1, we cannot say those two are concurrent because this happened much later. But basically the meaning of concurrency is that they don't know about each other, right? So if they don't know about each other, that means these two operations like are kind of concurrent, although it actually happened much later. But if they don't know about each other, then they are concurrent. So if client A and client B don't know about each other's operation, then I think they are concurrent. Okay, so yeah, so probably I think we need to we need to look deeper into these things, what these Lamport timestamps exactly are, what and these like we need to understand one of the total order broadcast protocols to exactly understand how they are implemented and how things are done. And probably we should do it in one of the Wednesday session. Yeah, but meanwhile, so I think it's 8:43. So I don't know if we should move forward. So the next section is distributed transactions and consensus. So like first distributed transactions are discussed in this chapter. So basically distributed transaction is that like we have seen this various scenarios, right? Where there are two databases and something should succeed only when it succeed on both the databases, on both of those different databases. So we have in the chapter of transaction, chapter 7, we have discussed that how the transactions could be done on a single node system, right? And basically the transactions should have this acid property that they should be atomic, right? That either the transaction should fully be successful or fully be failed. And then if concurrent transactions are happening, they should be isolated and the transaction should be durable, right? So that all we have seen how to do it in a single system. But it becomes much harder when we have to implement transactions in a distributed system. When your transaction gets completed, when the things get completed on two different nodes. Because like imagine this scenario that you're right, you have successfully written the data on one of the nodes, right? And now when you were writing data to other node, then something failed. So now this, before you are going to revert back the value in this database, someone might read the value from this database, right? So but we have seen that in a lot of scenarios we need this distributed transaction. And like these examples, could be like a booking kind of a system uh, where let's say a booking would be completed once the database where the payment has been made, that is successful, and once the seat is being able to deserve. So you might have one database for reserving seed, which is owned by some team, and then other database of making payments, right? So when both of these transactions get succeeded, then only the thing should be successful. So those are the scenarios where we need this distributed transaction kind of concept. But again, like when we will discuss it more, distributed transactions are expensive. So that's why a lot of systems don't actually choose distributed transaction, but they choose some weaker forms and some alternate. So basically, like in this case of booking scenario, something that would happen is instead of doing distributed transaction, which is expensive, like we will we will only book the seat, and we will assume that the payment would be made. So we will give user some time to make the payment, and if his payment was unsuccessful, then we will revert the value. But for some time, that seat will be reserved for that user. But imagine a scenario where we want to do something only when it gets succeeded in both of the databases. Otherwise, we need to fail it. And otherwise, anyone else should see the value as empty, right? Otherwise, anyone else should be able to reserve that seat if someone has not paid. In those kind of scenarios, we will actually need this distributed transaction. So one of the protocol which has been discussed is this two-phase commit, which is a very common protocol to implement distributed transactions. Uh, and yeah, so basically, like a brief explanation of this is, so basically there is a coordinator node uh, which will be implementing two-phase commit, and these are the two databases. So this two-phase commit happens in two phases. That once the two databases, they will be asked that are you ready to write the data. So if both response okay, then in the next step, so then in the next step, this phase one starts, where you ask both the databases to prepare. So you ask them to prepare and to write the database. And once they have responded yes, then you ask them to commit the value. So the point is that up till this point, when you initially ask them to write the some value, at this point, if any one of them responds with no, right, then the transaction is aborted. And up till now, you have not written any value in the system, like none of the value is committed, right? Now, let's say in this prepare phase, right? In this prepare phase, if this node responds yes, and if this respond has failed, this respond has not responded, and there is a timeout or something, then again, the transaction will be aborted, right? And the transaction will be aborted, and still nothing has been written to these two databases. But once they both say yes, once they both have responded yes, then the coordinator will store with itself that these two databases have agreed to commit the value. So now these two databases should actually commit the value. And now, after this point, after this phase one, there is no option to go back, because it has been agreed upon. So both the database has to commit the values, and if one of the database goes down, it is the responsibility of coordinator to keep on retrying. So the coordinator will keep on retrying again and again until the databases come back again, and uh, and so and to eventually make both the databases commit the value. So yeah, so this is how the two-phase commit is implemented. So let's look at these scenarios one by one. So we said when both databases agree to write the data, then the prepare stage start, then the commit starts, right? Up till these two states, if one of the database does not return, we can abort the transaction. So in the commit stage, but in the commit stage, if one of the machine dies, whenever it wakes up, it must first complete the transaction it has agreed upon. So if this machine dies before actually starting respond to the customer request, first it has to complete the transaction that it has agreed upon. So for that time being, that node will be available. And during that time, the coordinator will keep on retrying. So like these are the various steps that when application wants to begin transaction, it requests the transaction ID from the coordinator. So it will request a transaction ID. The application begins single node transaction on each partition and attaches that global transaction ID to each node. And up till this point, anyone can abort, right? When the application is ready to commit, coordinator sends prepare request to all the nodes with the transaction ID. If any of the request fails, coordinator sends abort for that transaction ID. When coordinator accepts prepare request, it makes sure it can definitely commit transaction under all circumstances. Participant has made a promise, but not yet committed. So at this point, both the participants have made the promise, but they have still not committed the value. So when coordinator receives response from all prepare request, it makes a definite decision on whether to commit or abort. The coordinator must write this decision to its transaction log on disk so that it knows which way it decided in case it subsequently crashes. This is called the commit point. So this point is called commit point. Once the coordinator writes to the disk, commit or abort requests are sent to all the participants. And then coordinator must keep on retrying forever until it succeeds. So the two crucial points of no point of return are when participants have voted yes here at this point, right? When they have voted yes, they have promised they will be definitely be able to commit later. So at this point, they both have agreed to commit. So now they just need to wait for the coordinator to tell them that they can commit. But now they have agreed that they can definitely commit the value. And the coordinator, how it will make the decision whether the value should be committed is based on if it got the response yes from both of the databases. If it got response yes from both the databases, it will ask it to commit. If it got a response of no from one of them, it will ask both of the databases to abort the transaction. Right?
Okay, could you scroll back a little bit to the picture? Let's see. So, okay, can you scroll up one more, a little bit more? Yeah, right there. Yeah. So let's say when it say, commit. Let's say the coordinator say commit, and then let's say the database 2 accepted, but it before it send the response, the okay back, it crashed. And did you say that like the coordinator have to keep trying?
So what point it failed?
At that point, like in the middle of it commit on the database 2 and database 2 crash, then
was it able to actually commit the value and not respond okay, or are you saying it was not able to commit the value like this?
It's in the middle of commit, not like right in the middle.
Right
Yeah,
in the
it received the commit request and the process half of it, and it crashed.
So
So
yeah,
did you say the coordinator have to keep trying?
yeah. See, because the thing is, if this node has crashed, right, then nobody can access the value from this node. And whenever it is alive again, before accepting the request, first it has to talk to the coordinator and it has to check whether there were any pending commits it has to make. So then in this case, it will see that this is the commit which it has to make. Once it has made that commit, then only it can start responding. So yes, the coordinator will keep on retrying until this node is alive again. And once this node is alive and it has committed the value, then only it can be made available.
Okay, but the coordinator have not received the OK from database 2 yet. So would that mean like, the transaction have not been committed?
So
I
if
mean, not been completed.
if the data, if this OK is not, if the coordinator does not get back this OK response, right? So what that means is that the value is committed here, right? But the coordinator will keep on retrying. But that is okay, right? Because uh, the value has been committed, and even if the coordinator retries, like we will see that this value has been committed. So then in the retry, we will respond okay back to the coordinator. But if we don't get back the okay response at coordinator, still the value has been committed, which is okay, right? Because we are saying at after this prepare stage, if the coordinator has send you commit, you have to commit the value, and the coordinator will definitely make a decision at this point. So at this point, coordinator will make a decision, and that decision it will store in the permanent storage with itself, whether that request should be committed or aborted. And that decision will be sent to both the databases.
Okay, yeah. But that, see how long the lock held by transaction, right? Let's
Yeah.
see. Yeah, that this is only 2 database we need to commit. But if we have, 3 or 4 database, then the lock held by transaction will be longer and longer, right?
Yep, yep. And like this coordinator is like kind of acting like a single point of failure that this coordinator has to manage. So that's why like this is what has been mentioned, right? That this two-phase commit is expensive. And that's why like it is like it should be like we should think considerably before implementing two-phase commit. And if we are implementing it between different databases, like which are not of this same, like which are not the same database, but if we are externally, so in some scenarios the database themselves implement two-phase commit if they are providing this distributed database service. But if we are implementing two-phase commit on different databases, then it could be even slower, and we could have even uh, we could even have harder uh, performance penalty than if the we are using homogeneous database, which is where this is implemented by the database manufacturers.
Abhishek, I have one question related to the example you gave, but I think we're almost at time. Like, I will briefly touch, maybe next time we can discuss the example you gave, like for the booking system, right?
Mhm.
Books of first booking and then the second DB will be payment.
Mhm.
But that, can we implement that at the server level? Like, if both are successful, then success, otherwise we can abort. Do we need that at the DB level?
So it has to talk to database to know, right, that if both are successful. And
so that can happen, right? Server file first say like the booking, once the booking is done, then it will issue the payment request. Once the payment is done, if let's say if payment failed, then we can abort the previous booking request, like
But-
abort the previous.
see, but either you would have to book the seat in the database to know for sure. Like, let's say you just looked at the value and you saw that the seat is empty, right? And you are saying, okay, I can book the seat. Now let's proceed to payment. What if you made the payment and now that seat was reserved by someone else? So either you have to make the change in the database that now I'm going to reserve the seat. So now you have reserved the seat and still you have not made the payment. And basically if the payment failed, for that time you have reserved the seat which could have been actually used by someone else, right? So I'm saying the requirement is you have to strongly implement the system which is a distributed transaction, that the booking should only complete when both of the things are successful. Otherwise the seat should be left untouched. Seat should be left
Abhishek, just a time check. I know like this, I don't know whether you will be able to complete this in few minutes, but
I think we can discuss Abhishek next time. Thanks.
Okay.
Yeah, thanks, Abhishek. Yeah.
okay, Abhishek, can you make Bhavesh or myself one of them as a host?
Yeah. Bhavesh is co-host, and let me make you.
I put
I
the
assume.
CoderPad link.
Okay. So we will use this for the discussion, right?
Yeah, like how we did last time.
Okay.
I can see Bhavesh is there.
Can we stop this recording and start a new recording?